Hopefully this sound works. I know on the last video it didn't work so well. Okay, so I want us to remember the front of this page is just review. None of this is new. So we have that KW, this will be important in a little while. KW is equal to 1 times 10 to the negative 14. That's just the ionization product constant for water. It's always that exact same number. Here we have the pH equation, the pOH equation, the pH and pOH equal 14. We also have how to find H concentration from pH and how to find OH. These are all in that little square box that some of you took a picture of or wrote down. If you have issues, let me know. Down here at the bottom, it's just reminding us that pH below 7 is acidic, pH above 7 is a base. Okay, so this is just old information. We're going to go ahead and calculate pH, however, from our H concentration. If you don't remember, in order to find pH, we take the negative log. So when I take the negative log of 5.4 times 10 to the negative 4, I get 3.27. And then when I subtract that from 14 to get pOH, I get 10.73. When we're going the other direction to the concentration, that's when we use second log. Oh. And I get 1.86 times 10 to the negative 11. Okay, if you recall, when the pH is less than 7, it's an acid. So here, this is an acidic compound. Okay, we're going to move on. If you should probably practice this box on your own, but it's just a review. Let's go ahead and calculate the pH of nitric acid. Remember, nitric acid is a strong acid, which means that it breaks apart completely. So nitric acid breaks into hydrogen ion and nitrate. So in order to find the pH, I take the negative log of the concentration. And that gives me 1.37. So that is my answer for pH. As we're moving on, we're going to find the pH from a base. So this does require a few more steps. Also notice there's going to be 2 OHs because barium has a +2 charge. It's still strong because group 1 and 2 metal hydroxides are strong. This is where that worksheet from last night's homework comes into effect, where you have the ones where you're breaking the concentration for the compound down into their ions. So if I have 1 BaOH2, then I have 2 OHs. So that makes the OH concentration in this situation 2 times the original concentration. So it's 0.04 molar. I cannot go straight to pH from here. I do know how to find pOH from here. The negative log of this, which is equal to 1.40. In order to find pH, remember we do 14 minus pOH, and I get 12.60. Just remember, if you have any questions, let me know. This page does actually apply to what we learned in the previous lesson that you watched a video over. So this is where we're talking about weak bases and weak acids, and we're going to do an ICE table. So this question says calculate the pH and percent ionization of acetic acid. Remember, step 1 is to write the initial concentrations. So my initial concentration is 0.250. And like I said in the previous video, if all we have are reactants, there should not be any products. The next step should be to do the change concentration, or the change in concentration, with an X. Remember, we're going to subtract X from the side that we have numbers on. We're going to add X to the side where there's nothing there. And then we add them together. So I have 0.25 minus X. This is just X. And this is just X. So the next thing we should do is just go ahead and plug it into our equilibrium expression. Remember, it's products over reactants. So it should be the concentration of H times the concentration of acetate divided by the concentration of acetic acid. Remember, these are all equilibrium concentrations. And up here it told us what the Ka is. The Ka will be different for every compound, but acetic acid happens to be 1.8 times 10 to the negative 5. So then I'm going to go ahead and plug my numbers in. So I have X and X on the top. And then at the bottom, remember I told you we're going to get rid of the minus X, so it's just 0.25. At this point, we're just solving an algebra problem. So we multiply our two numbers together, and I get that X squared equals 4.5 times 10 to the negative 6. In order to find X, I need to square root both sides. So X equals 2.12 times 10 to the negative 3 molar. Remember, at this point, you need to go ahead and tell me what concentrations this is equal to. Sometimes it will not be equal to two things, but here it does happen to be. Okay, this is not our final answer. It did not ask for the H concentration. It asked for the pH. I can find pH by taking the negative log of 2.12 times 10 to the negative 3, because I had no concentration before of H. And I get that the pH is 2.67. So that is one of our answers. It also asks that we find the percent ionization. Remember, that's just part over whole times 100. If you look back at your notes, though, it's the concentration of H at equilibrium divided by the weak acid's concentration initially times 100. And we should get that it's 0.848%. Remember, this is a very small amount, so only 0.84% of our acetic acid broke up into its ions, which is a very small amount. I am going to skip number 5, but I do need you to note that this is a KB problem. Remember, KB finds an OH concentration, which means I cannot go directly from OH to pH. I'll have to find POH first. Then I can solve for pH. But it's exactly the same as we did the last one, except this time we're finding OH instead of H. I do want to work this second one on this page because it doesn't have an ICE table like the other two had, so this is going to be more like your homework is. Notice on this one there is no, it doesn't give me a KB value. It doesn't even have an equation. In the situation where there's no equation, we can go back to the previous page on page 3 and find just the base generic equation. But it does look like this, where I represent base with B8 or B, then I add water, and the water is acting as the acid. The water is going to give an H away, and then we're going to make OH, which is what we need. In this situation, when I don't have an ICE table already made, we just draw ICE on the side, and we plug in our initial value, which is 0.1. Notice it says of a weak base. Our base is represented by B, so that's where it goes. Water is a pure liquid, so we don't care about it in an ICE table. And these always start out at 0. Okay, for our x, we just do minus x, and then we add them. So 0.1 minus x, x. At this point, we need to go ahead and plug our stuff into our equilibrium expression. So Kb is equal to products over reactants. So I have x squared over 0.1. Remember our minus x, it goes away. The problem with this is I have two variables and I don't have a way to solve that without knowing what one of those two variables are. I do, however, have the pH that the problem gave me. From the pH, I cannot find either the I cannot find the OH or the BH concentration, but I can find the pOH. So pH is so 14 minus pH is equal to pOH, which is equal to 4.33. At this point we can find OH. Remember, we do that by doing the second log of the negative pOH. This happens to be 4.67 times 10 to the negative 5. And since this is our OH concentration, this is one of these x's, but it is also the other x because they're the exact same thing. So my Kb equals 4.67 times 10 to the negative 5 squared divided by 0.1. When I do these calculations, I have Kb equaling 2. We only have 2 sig figs. Please note there's only 2 sig figs. That's because at the top the 0.10 only has 2. 2.2 times 10 to the negative 8. Remember, Kb does not have any units. None of the equilibrium constants do. Page 5 is just some information that you need to look at. Some of our main things are that here I have that Ka times Kb equals Kw, and Kw is always this number just like it was on the first page. Similarly, the pKa can be found by taking the negative log of Ka, just like we find pH by taking the negative log of H. So we're going down the page. It's just showing us the ionization constants and how Kw is equal to Ka and Kb. Alright, I did already write some information on this page that you need to go ahead and copy down. So if you need to pause at this point to write this on there, that's fine. But the first one says the larger the Ka, the stronger the acid. So question A on 7 asks which of the following acids is the weakest. If the bigger Ka is the strongest, then the smallest Ka is the weakest. I hope by looking at these 3 Kas you can see that HCN is the weakest because it has a negative 10 exponent, which makes it much smaller. The next question asks about which one is the strongest base, and this has to do with conjugate bases. So I did already say the weaker the acid, the weaker the conjugate base, and we did briefly discuss that in the notes that we did at the beginning of acids and bases, but that's been a little bit. So our weakest one would have the smallest value. Our strongest one would have the smallest value. So that would be this one that has the smallest value, which would make that one our strongest conjugate base. The pKa is equal to the negative log of the Ka. So I'm just going to take the negative log of the Ka of HCN, which is 4.9 times 10 to the negative 10. And I get 9.31. And then to find the KB for Cn, because these two correspond via KW, you take KW, and we're going to divide by the KA to find KB. For those of us that struggle with solving that equation, KB is equal to KW over KA. I don't really feel like that's a very hard equation to rearrange because you're only moving one variable. But if you need help, let me know. The answer to this is 2.04 times 10 to the negative 5. Remember, KAs, KBs, KW, they have no unit. I hope you've learned some from the video, and we'll discuss this when I get back.